Hi, welcome back to my class in number theory. For today, we will take more examples for using mathematical induction in proving. And consider the first example for today. Prove n factorial is less than equal to n to the power n for every n element of n. Capital N here is the set of natural numbers or the set of positive integers or the set of counting numbers. And so a small n here is a positive integer. The smallest of the positive integers is 1. And we want to prove that n factorial is less than equal to n to the power n. And we will prove this by mathematical induction. As in our example last lesson, in the first part of the proof by mathematical induction, we must show that this mathematical statement n factorial less than equal to n to the power n is true for the smallest positive integer or smallest natural number n is 1. For n is 1, we start from the left-hand side of this mathematical statement. N factorial is equal to n is 1, 1 factorial. And 1 factorial is 1. And at the right-hand side of this mathematical statement, we also compute n to the power n, for n is 1. N to the power n when n is 1 is equal to 1 raised to 1. And 1 raised to 1 is 1. Thus, the left-hand side is n factorial is 1. And the right-hand side, n to the power n is also 1. And this mathematical statement is satisfied for the equality part of this mathematical statement because 1 is equal to 1. Thus, we write n factorial is less than equal to n to the power n for n equals 1. In particular, n factorial is 1 and it's equal to n to the power n, 1. In particular, we have shown in the first part of the proof by mathematical induction that n factorial equals n to the power n and both are equal to 1 for n equals 1. Now, the second part of the proof, we assume that this mathematical statement is true for n equals k. For the second part of the proof, we assume that this mathematical statement n factorial less than equal to n to the power n is true, is satisfied when n equals k. When n equals k, you replace n with k, you get k factorial less than equal to k to the power k, where k is greater than equal to n and n is greater than equal to 1. Because n is a natural number, the smallest value that n can take is 1. And we will use this assumption to prove that this mathematical statement is also true for n equals k plus 1. And this assumption is what is known as the induction hypothesis. Again, we will use this assumption or this induction hypothesis to prove that if n equals k plus 1, then this statement is also true. This is what we want to prove for the second part of the proof by mathematical induction. We want to show that if n equals k plus 1, this mathematical statement is also true. When n equals k plus 1, n factorial becomes k plus 1 factorial less than equal to n k plus 1 to the power n k plus 1. And to prove that this is true, we will use the induction hypothesis that k factorial less than equal to k to the power k is true. We start from the left-hand side of this inequality. We expand k plus 1 factorial by definition of factorial. By definition of factorial, k plus 1 factorial is equal to the product of all the positive integers from k plus 1 up to the smallest positive integer 1. Hence, by expansion, k plus 1 factorial equals k plus 1 multiplied by k multiplied by k minus 1 by definition of factorial, the expansion of k plus 1 factorial equals k plus 1 multiplied by k. The positive integers are decreasing by 1. And k minus 1 times up to times 3 times 2 times 1. But the product from the positive integer k up to 1 is k factorial. Again, the product k times k minus 1 times 3 times 2 times 1 in compact notation is equal to k factorial. And we write k plus 1 factorial equals k plus 1 multiplied by k. The product k up to 1 is k factorial. Hence, k plus 1 factorial is equal to k plus 1 multiplied by k times k minus 1 times up to times 3 times 2 times 1 we replace by k factorial. Now we obtain k plus 1 factorial equals k plus 1 multiplied by k factorial. Now we will make use of our induction hypothesis or our assumption that k factorial is less than equal to k to the power k. And this k factorial by our induction hypothesis is less than equal to k to the power k. So if we replace k factorial with k to the power k, the product k plus 1 times k to the power k would be less than k plus 1 factorial, because k factorial is less than equal to k to the power k. We write k plus 1 multiplied by k factorial, we replace with k to the power k. And this product, k plus 1 times k to the power k is greater than equal to k plus 1 times k factorial. Or this product, k plus 1 times k factorial is less than equal to k plus 1 times k to the power k, because this k factorial is less than equal to k to the power k. Now if I add 1 to the base k here, we would like to obtain an expression of this form, k plus 1 to the power k plus 1. And we have k plus 1 here, the exponent is 1. And I want to write this k as k plus 1. I want to write this exponential notation with the base of k plus 1 to the power k, so we can combine it with k plus 1 to the power 1. Now, I said if I write k as k plus 1, then this product would be less than, we write k plus 1 to the power 1. I simply specify the exponent of k plus 1, it's 1. And I will add 1 to k. I will write k as k plus 1 to the power k. Now this product, k plus 1 times k to the power k is less than k plus 1 multiplied by k plus 1 to the power k, because the base of this exponential notation, the base k plus 1 is 1 more than the base of k to the power k. So this product is less than k plus 1 raised to 1 multiplied by k plus 1 to the power k. And so we have k plus 1 factorial is less than k plus 1 raised to 1 times k plus 1 to the power k. Again, k plus 1 factorial we have shown is less than k plus 1 raised to 1 multiplied by k plus 1 to the power k. And we apply the property of exponent from your course in algebra to multiply these two. With common base of k plus 1, we add the exponents of 1 and k. Hence, k plus 1 raised to 1 multiplied by k plus 1 to the power k is equal to the common base k plus 1. To the power, we add the exponents 1 plus k, or by commutative property of addition, k plus 1. We have shown that this mathematical statement is true. K plus 1 factorial less than equal to k plus 1 to the power k plus 1. In particular, we have shown that k plus 1 factorial is less than. This is still satisfied because we have less than here. Less than k plus 1 to the power k plus 1. Now we write our conclusion for the second part of the proof. Our conclusion for the second part of the proof by mathematical induction, we have shown that n factorial is less than equal to n to the power n for n equals k plus 1. That is, we have shown that if n equals k plus 1, replace n with k plus 1, k plus 1 factorial is less than equal to, replace n with k plus 1, k plus 1 to the power n k plus 1. Particularly, we have shown here earlier that k plus 1 factorial is strictly less than k plus 1 to the power k plus 1. We write particularly, we have shown that k plus 1 factorial is less than k plus 1 to the power k plus 1. Therefore, we conclude that the given mathematical statement n factorial is less than equal to n to the power n. For every n that is a natural number or positive integer. We have shown that the mathematical statement n factorial is less than equal to n to the power n for every natural number small n. And we write this shaded bar or rectangle to indicate the end of proof. We take another example in using the mathematical induction to prove that 2 to the power n is greater than equal to 5 times n for natural numbers or positive integers n greater than equal to 5. For the first part of the proof by mathematical induction, the smallest we assign n, the smallest natural number or the smallest positive integer 5. Because we are given this condition that this mathematical statement is only true for natural numbers that are greater than equal to 5. Therefore, the smallest value of n, the smallest value that n can take is 5. And we assign n equals 5 for the first part of the proof, and we show that this is true. For the first part of the proof by mathematical induction, we take n equals 5. For n equals 5, we show 2 to the power n is greater than equal to 5 multiplied by n. Hence, we start with the left-hand side. For n equals 5, 2 to the power n becomes 2 raised to n, and n is 5. 2 to the n is 2 raised to 5. And by definition of exponential notation or exponential form, 2 raised to 5 means that you multiply the base 2 by itself 5 times. And if you multiply 2 by itself by 5 times, or simply use your calculator to calculate 2 raised to 5, and you should get 32. And we also compute the right-hand side, and we show that this left-hand side, 2 to the n, the value of 2 to the n at the left-hand side is greater than or equal to the value of 5 multiplied by n at the right-hand side. We have computed the left-hand side 2 to the n, and it's equal to 32. Now we compute the value of 5 multiplied by n, where n equals 5. If n is equal to 5, the right-hand side, 5 to the n becomes 5, multiplied by n is 5, and 5 multiplied by 5 is 25. And you can see that 32 is strictly greater than 25, which means that this inequality sign is satisfied. And we conclude that 2 to the n is greater than equal to 5 to the n if n equals 5. More specifically, we have shown that 2 to the n is greater than, strictly greater than 5 multiplied by n if n is 5, because 32 is the value of 2 and 32 is strictly greater than the value of 5n, which is 25. Our conclusion for the first part of the proof, by mathematical induction, we conclude that 2 to the n is greater than equal to 5 multiplied by n if n equals 5. Particularly, we conclude that 2 to the n, which is 32, is strictly greater than 5 to the n, which is 25, if n equals 5. Now we go to the second part of the proof by mathematical induction. In the second part of the proof, by mathematical induction, we state our induction hypothesis. And the induction hypothesis is that this mathematical statement 2 to the power n greater than equal to 5 multiplied by n is true for n equals k. For n equals k, we assume that n is k, replace n with k, you get 2 to the power k greater than equal to 5 multiplied by n is k, 5k. We assume that this inequality is true, that is 2 to the power k is greater than equal to 5 multiplied by k, where k is greater than equal to n and n is greater than equal to 5. And using this induction hypothesis, we show that for n equals k plus 1, now replace n with k plus 1. You get 2 to the power k greater than equal to 5 multiplied by n, replace n with k plus 1, 5 times k plus 1. We want to prove now that 2 to the power k plus 1 is greater than equal to 5 multiplied by k plus 1. And we obtain this statement from this given mathematical statement for n equals k plus 1. And we will prove that this inequality is true using our induction hypothesis 2 to the power k greater than equal to 5k. We assume that this is true, and we will use this to prove that this inequality is also true. To prove that 2 to the power k plus 1 is greater than equal to 5 times quantity k plus 1, we will start from this our induction hypothesis. And from this induction hypothesis, we will try to come up with this inequality or mathematical statement. We have 2 to the power k greater than equal to 5 multiplied by k. Because we want the exponent of 2 to be k plus 1, I will multiply both sides of this inequality by 2 to the power 1, so that we can combine 2 to the power 1 with 2 to the power k by property of exponent from your course in algebra. And the inequality sign greater than or equal to will remain as is, because by multiplication property of inequality, if you multiply both sides of inequality by a positive real number, the inequality sign remains the same. So we multiply the left side by 2 raised to 1. And we multiply the right hand side by 2 raised to 1 or 2. And the inequality sign remains true, because we multiply both sides by positive 2. Now we can combine these 2 by property of exponent. The common base is 2. And we add the exponents. 1 plus k is equal to k plus 1 by commutative property of addition. And 2 to the power k plus 1 is greater than equal to 2 multiplied by 10, multiplied by 5k or 10k. 2 multiplied by 5k is 10k. Now we now have 2 to the power k plus 1 at the left hand side. greater than equal to 10k, but we want 5 times quantity k plus 1 at the right hand side. And we must show that this inequality sign is still satisfied. Now 10k can be written as 5k plus 5k. Again, I have written 10k as the sum of 5k plus 5k. Now, I want this expression 5 times quantity k plus 1, and this expression is the same as 5k plus 5. But instead of 5, we have 5k here. Now, if I remove k here, if I simply write 5k plus 5, then this sum 5k plus 5k or 10k will be strictly greater than 5k plus 5. Because this now is simplified, but in this sum, 5 is multiplied by an integer k. So definitely this sum 5k plus 5k is greater than 5k plus 1. Therefore, we have shown here that 10k is greater than 5k plus 5. Thus, we have 2 to the power k plus 1. We now write greater than equal to 10k, but 10k, which is equal to 5k plus 5k, we have shown is strictly greater than 5k plus 5. Hence, 2 to the power k plus 1 is greater than 5k plus 5. Strictly greater than 5k plus 5. But 5 is a common factor of these two terms, so we factor out 5. Again, factoring out the common factor 5 from 5k plus 5, we get 5 times quantity k plus 1. Thus, we have shown that 2 to the power k plus 1 is greater than 5 times k plus 1. We therefore have shown that the original mathematical statement given 2 to the power n we have shown that the mathematical statement 2 to the power n is greater than equal to 5n if n is equal to k plus 1. If n is k plus 1, we have 2 to the k plus 1 greater than equal to 5 times k plus 1. More specifically, we have shown that if n equals k plus 1, 2 to the k plus 1 is strictly greater than 5 times k plus 1. Still, this inequality is satisfied. Now, we combine the results from the two parts of the proof by mathematical induction to make now our conclusion. therefore conclude that the mathematical statement or this inequality 2 to the power n is greater than equal to 5 times n for every natural number or positive integer that is greater than or equal to 5 is true. And this shaded rectangle indicates the end of proof. For your practice, please try the following exercises. Prove, and you will use mathematical induction for the following exercises. In number 1, you prove that 2 to the power n is greater than 6 multiplied by n for natural numbers n element of capital N, the set of natural numbers are positive integers, and the positive integer n is greater than equal to 5. In number 2, you are given the condition that 0 is less than a and a is less than b, or b is greater than a and a is greater than 0. And you try to prove by mathematical induction that 0 is less than a to the power n, and a to the power n is less than b to the power n for all natural integers, or for all natural numbers, or for all positive integers. That is, for every n element of the set of natural numbers. And that completes our lesson for today. If you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calizon, the channel of learning and leisure. Or you may ask your friends and classmates to subscribe to my YouTube channel, Art Calizon, so they may learn as well. Thank you for joining me in my class today.